Okay, earlier we discussed Gauss's law, and we discussed it in integral form. This time we're going to stay on Gauss's law, but we're going to do it in differential form. So let me just write out that expression. It basically states that the divergence, which is represented by the del dotted with the electric field, is going to be equal to the charge density divided by epsilon naught. And I should probably make that a little bit more clear that it's a rho. So this is evaluated at a point in space. So when we talk about the charge density, we're talking about evaluating the divergence of the electric field at a point in space, and it's going to ultimately give us the value of any charge in that area. So if we run the divergence of an electric field in a charge-free area, we expect that answer to be 0. However, if we do the divergence in an area that has charge, like let's say in an insulator, and in our previous example we used a sphere that actually had a charge assigned to it, then we would expect to get a non-zero value, and it should work out to be equivalent to that charge density based on that volume. So the first thing that we're going to need to evaluate this is a good expression for that electric field. So we go back to our previous example, and if I can just use a little cut and paste magic here, this is the electric field that describes the field given to a charge distribution of a uniformly charged sphere. It's very similar to a point charge. If you remember in the example that we built in Maxwell in the computer simulation, we have no way of representing a point charge, so we used a small sphere as something equivalent and representative. So we're going to build off of that example later on, and we're going to show that we can verify this divergence analytically by using this equation. We have two different forms here. One is describing the electric field anywhere outside at an arbitrary distance r from the center of that sphere. So as long as we're not inside the sphere, this would mean that we are actually out in a free charge region. Okay, whereas this other one is defining the charge inside that sphere. Now remember, this is an insulating sphere, and it's not a conducting sphere, so it follows quite different rules. But you'll notice that in this example, the r naught is actually the radius of the sphere, and r is a distance between the center point of that sphere and the radius of the sphere. So it does take a little bit of a different form, and we'll see as we evaluate this, we're going to get different results. So now that we have a electric field that describes the field from a charged insulating sphere, we need to know what the divergence operator looks like in spherical coordinates. So for that, we're going to use this definition of the divergence in spherical coordinates. So it looks a little intimidating at first until you recognize a couple of really convenient things about the equation that we have for an E field here. So what this is saying is that the divergence on A is going to map into these various expressions for the representative orthogonal components. So we've got an r hat component, we've got a theta hat component, and then we also have the phi hat component. So the AR, A theta, and A phi are really representing those portions of the vector field A. So in our example, we know that our vector field is defined by this E right here, and we're going to choose one of these. We're going to start with evaluating the electric field outside of the sphere. So if you look closely at this equation, what you see right out of the chute is that there's no dependence on theta or phi at all. Rather, the only component is going to be that r hat component. So what that means is that when we apply the del dot to E instead of A, we're going to be able to ignore these components. So I can either delete them, or I can maybe just draw, maybe I should just cancel them out, because we know that there are no theta and phi components to our equation. So what we have to do to evaluate the divergence is substitute AR with basically ER, which is the entirety of this function. So to be more clear, if we want to evaluate this expression, we're just going to look at the left-hand side. We have to have the E, so we completely have that over here as the red component, and then we have to have the divergence. And that divergence operator is the del dot, which is completely represented by this portion right here. So we're going to substitute this instead of AR. We're basically going to replace this with E. And I know that looks pretty sloppy as I write it on there, but that's basically all we're doing is replacing it with this component. So let's have at it. So we can write this out, and I'll just repeat those steps. So let's write out the divergence, and over here I can say del dot E is going to be equal to, let's just copy this component down. We know we have to put 1 over r squared. We'll write that down. Now we have to represent the partial derivative of this thing in brackets. So let me just write that out first. The partial with respect to r. And I'm just going to, just to make it clear, we're going to go ahead and make a large bracket here where we can actually put that equation in there, or that expression. I should probably make it larger than that. So let me. So in the brackets now we have to remember to put this r squared. That's by definition of the del dot in spherical coordinates. So we're just going to write r squared. And now let's copy the E component. So it's going to be 1 over 4 pi epsilon naught. And then we can say Q over r squared. Okay, and we're going to close this off. We know that we just took the r component. So the dot product between the vectors of r hat and the r component have already taken place. We could just ignore those. If you wanted to be more explicit, we could have an r hat for this component that was dotted with an r hat coming from the del dot operator. But we're just going to ignore that, knowing that has worked out to a unit vector dotted with a unit vector equals 1. So this is our entire expression here. And let's just keep carrying this through now. So if we look at the things that are constant here, we can take those all the way through. So let's go ahead and do that. We'll go ahead and just copy out 1 over r squared, and then r squared is not constant, but all of this 1 over 4 pi epsilon naught is constant, and this capital Q is also constant. This denominator of r squared is not. So let's go ahead and bring the Q out. That's the total charge on the sphere. And then 4 pi epsilon naught. And then I think I have everything. And then now it's the partial with respect to r of this r squared in the numerator and this r squared in the denominator. So you've already recognized that this is going to reduce down, even though these are not constants. We know that r squared divided by r squared is going to equal 1. So if I cancel these out and replace that with 1, then we know that this is going to equal, let's just go ahead and, just to be completely clear, I won't skip any steps, r squared q over 4 pi epsilon naught with the partial derivative of 1. Well, we know the number 1 is nothing more than a constant, and we know from our derivative rules that any derivative of a constant is going to be equal to 0. So that basically means that this whole expression comes down to 0. So what we essentially said was that the divergence, this thing on the left-hand side, which is supposed to equal the charge density divided by epsilon naught, is going to equal 0. So we just solved the left-hand side for a point outside of the sphere, and we know that that is also equal to the charge density divided by epsilon naught. And if the charge density is the charge per unit volume, then that's basically telling us that the charge, I can just rearrange this to say, if I multiply both sides by epsilon naught, I end up with 0 on the left-hand side, which means 0 is going to equal rho. So all this tells me is that by running the divergence of this expression, which represents the electric field outside of the sphere, it's telling me that the charge density at a point outside the sphere is 0, which actually makes perfect sense because all of the charge is contained inside the sphere, and we're evaluating a point on the outside. Okay, so let's continue on. We'll remember that this solution was for outside. Now what we're going to do is we'll take this part. So if we just run that exact same operation, but now let's look at this formula for the electric field residing inside a sphere that has radius r naught, and it has a total charge distribution of q. So let's just run through the whole thing again. We'll use the whole space down here. We should be able to get this all in. So we'll say the divergence of E is going to equal 1 over r squared, partial respect to r, and I'll make it a larger bracket so I can get everything in here. I have to copy the r squared, okay, and then now I'll just completely copy over this formula. So I'll just, or I should say expression, 1 over 4 pi epsilon naught r naught cubed, and then I can, let me just extend this, and I can put the q up here as well as the r. And I'm not going to put the unit vectors anymore because we did the dot product already, so we know that that comes out to 1 because we only have the r component. And that's exactly what we wrote down. So with that, I'll close that off. We'll do the usual thing where we will bring out all of the constants. So I'm going to pile the constants up on the far left. So let's just say equals, and let's grab all the constants. That's a 1 times q. So q is a constant. In the denominator, we have 4 pi and epsilon naught. We also have r naught. We know that r naught was the radius of that sphere. So let's go ahead and bring that whole thing out. So we'll say q, capital Q, divided by 4 pi epsilon naught r naught cubed. Okay. We have to remember to write the 1 over r squared, which is before the derivative. So we'll say 1 over r squared. And then now let's go ahead and take the partial derivative. Well, I'll just set it up. We won't take it yet, but we'll say partial with respect to r of, it looks like we have basically the r squared times r. So we know that that's going to be r cubed. Okay, we'll copy this over again. So all the constants, nothing's changed. We'll say capital Q divided by 4 pi epsilon naught r naught cubed, and then 1 over r squared. And now let's go ahead and take the derivative. So we know from our differentiation rules that the partial derivative with respect to r of r cubed is going to be we basically take the 3 down and we multiply it by r to the power minus 1 in this case. So 3 minus 1 is going to be 2. So the derivative of r cubed is going to be nothing more than 3 times r squared. And if that looks unfamiliar to you, then you can review some of the handouts that we've given you on the rules for derivatives, and I believe that's referred to just as the power rule. So we've already taken the derivative, so that's exactly what that is. We can start to see how things might cancel out now. This is a multiplication sign. So r squared in the denominator with r squared in the numerator, that's going to cancel out. We can bring this 3 over. So if I rewrite this, let's go ahead and bring it over here. If I rewrite this now as, I can write it this way. I can say, let's say Q. I'm being a little strategic about how I do this. I'm going to say capital Q over epsilon naught right now. And now I'm going to organize everything else separately. So let's put the 3. That's all I have left in the numerator. And in the denominator, I have 4 pi r naught cubed. And one reason why I did it this way is because you're starting to see a familiar form with the charge over epsilon naught. But if you look at this a little bit closely, what you realize is that this has a very similar look to the volume of a sphere. And it turns out that if our sphere has a radius of r naught, then we know, you can look this up in any geometry book, I'll go ahead and just write it as a reference up here, is that the volume of a sphere is going to equal 4/3 pi times the radius cubed. So if you just look closely at this expression down here and what I just wrote up here at the top, it doesn't take long to realize that the similarities are that really this is just the inverse of that volume. So I can basically rewrite this. If I know that this is a volume, I can rewrite this as saying 1 over V. So if I said Q, which is divided by epsilon naught, times 1 over, that's supposed to be a 1 over volume of a sphere, I also recognize that the definition of rho, the charge density that you see in the beginning of our evaluation here, rho was defined as charge per unit volume. So this is really nothing more than rho divided by epsilon naught. And that's exactly what we were hoping to show, because we know that Maxwell's first law, Gauss's law, is telling us that the divergence of the electric field is always going to be equal to the charge density at that point divided by epsilon naught. We now have a formula which is different than the first formula, or I should say expression. We have an expression for the field inside that sphere, and we evaluated it inside the sphere where the charge resides, and it turns out we are getting exactly the charge density at that location. So it doesn't matter where we are inside that sphere. Anywhere inside the sphere, we're always going to evaluate the divergence of the electric field and come up with that charge density divided by epsilon naught. So we'll go ahead and remember this, and we should expect to get on the inside of the charged sphere, we'll get this value for del dot E, and then on the outside, we're going to get 0. So what we're going to do now is use the software, the finite element software, Maxwell 3D. We're going to use the exact same problem that you probably finished the first time, where we ran through validating Gauss's law in the integral form. So we had you go through the exercise of putting that charge on the sphere. We have a voltage that's been defined on the air box around it. So I won't review this in much detail, but this should be exactly where you left off in the integral portion. So if you completed that exercise, then this is the place that we're going to start. And just to verify, we actually do have fields solved. You should always see up in the top here, whenever you have a solved model, it'll show up at the very end of the title that it actually is solved. And we can convince ourselves that that's actually the case by looking at a quick field plot. If I just grab a plane, any one of these planes will be fine. I'm going to choose fields and electric field, and let's just do Maggie in this case. And we'll just leave all those defaults, and then we'll see that the distribution is as expected. You have a very large, a very high density of fields as you get towards the outside of the sphere, and you start to see it drop off. I can even hide some of these components on the outside. If you turn off the sphere itself, this actually also makes sense, because we should be showing that the fields typically go to 0 inside as you get closer and closer to the radius of a uniformly charged sphere, as long as it's an insulator. So this plot makes sense. I'll go ahead and turn these plots off from here on out. I just wanted to make sure that you were convinced that we actually have fields solved in this case. So I can go ahead and leave those vectors there, and I'll just say disable plot visibility. And now we'll go ahead and fit everything. I have to turn everything back on. So, all right, so with that, we're ready to open up the fields calculator, and we'll see if we can run the divergence at a couple of locations in here. But before we do that, I'm going to create a couple of points. So let's, if I select the air box, I can hit Control H to hide. I'm not going to worry about keeping these visible. I don't need that sphere. I'm going to hide all of this. And all I'm going to do now is I'll go ahead and use this box as a reference. If you remember, we set these boxes up before as non-model objects as ways to refine our mesh. So we should have a pretty decent resolution of electric fields anywhere inside this area. So I think what I'll do now is I'm just going to create 2 points. We're going to evaluate the fields, the inside of the sphere, and then we're just going to choose a location on the outside. So let's go to draw a point, and if you leave it in this mode, it should be able to sift out the center, and it kind of just sometimes you'll have to eyeball it, but I just went ahead and dropped the point right there in the center, and you'll see I've got a new tree that calls out the point. So there it is right there in the center. So there's my inside point object. I may as well go ahead and name it. I'll just rename it over here. We'll call it inside point. And then, as you probably already guessed, I'm going to go ahead and make an outside point. So let's just try to do it this way. If I get a head-on view, you can see that my plane is cutting right through the center of the sphere. So if I just do a head-on view here, let's go ahead and grab an area. Let's grab an area, far enough from the center of the sphere, but still in a pretty good high-resolution mesh area. So convince yourself that the point you created is kind of somewhere in the vicinity of that box that you see here. And certainly feel free to explore looking at different points outside. You'll probably see that the results are going to vary a little bit depending on the resolution of the mesh. Okay, we have our 2 points set up. I'm going to rename this one now, and I'll call this one outside point. And now we are ready to open Fields Calculator. So if we right click on Field Overlays, at the bottom we choose Calculator, and now we're going to start building up the stack. The first thing we're going to do is bring up the quantity of E field. So if you remember, we're basically going to be choosing from these categories of input some of the general functions, scalars, vectors, and output, and build up the stack to evaluate that the divergence at that point. So let's get started. We'll just choose quantity of E field. So we'll choose E, and then you'll see that that shows up in the stack right away. Now, the next thing we want to do is, since we have the E field loaded, we want to just take the divergence of the E field. So underneath vectors, the vector section, we hit the divergence button, and then now it turns into this form, which is indicating that it's a scalar, and there's the evaluation that's going to be done in the function call. Next step is going to be to choose the point in which we want to apply the divergence to. So to do that, we're going to go to the input geometry section, and we're going to choose point. And let's start by evaluating the inside point. Or I guess, to be consistent, we evaluated, we verified the outside in the analytical version. So let's start with the outside point instead. So we'll choose outside, okay, and with that, it shows up in the stack here. So I've got point, and I've got a scalar that are now going to be operated to combine a new function. And I'll do that by going to the value. So if I hit the value button, it's ultimately going to create this new function in the stack. So you should see something similar. So we know we're going to get a scalar, and all the function calls are embedded. So now when I hit the value button of this expression, I know that I am evaluating the divergence of the electric field at this particular point. Sorry, I should say the evaluate button. So now I have a number, and that's exactly what that equals. So remember what we're doing. If we go back to what we did analytically, we just calculated numerically this divergence of E. And we're saying that it equals this charge density divided by epsilon naught. We also know from our work down here was that the charge density, by definition, is the charge per unit volume of the sphere. We also know that the volume of a sphere is defined by 4/3 pi r cubed. So with all that information, we're almost done evaluating. We have the divergence calculated here, and now if we multiply by epsilon naught and by the volume of that sphere, then we should recover the charge that we initially assigned to the geometry. So let's go ahead and do that. So to multiply by epsilon naught, I'm going to choose constant. Epsilon naught is already one of the built-ins, so I'll go ahead and say multiply, and then I'm going to multiply it by the volume of the sphere. And I'm not going to do this in the calculator, but we know that that sphere that we set the charge on was 0.5 millimeter, and that equates to 0.0005 meters. So that's the number that we want to cube. So if we say 0.0005 cubed times pi times 4/3, we end up with a really small number of, I'll just go ahead and type it in. It's a constant. You can also calculate this as well. I'm going to use the number function here, and it's going to be 0.524 times 10 to the negative 9. This is meters cubed. So I'm going to say e to the negative 9. That's scientific notation for that number. And with those two there, as soon as I multiply these together, I should recover the charge at this location. And you'll notice it's very close to zero. It's not zero, and we can explain that because of numerical error that involves the accuracy of that calculation with the mesh that we gave it. But this number is very close to zero, and what we just did was we determined that the charge at that point that we called outside, if you remember, was outside of the sphere, is equal to approximately zero. which is consistent with what we calculated analytically for that expression, and which is what we just came up with numerically as well. All right, so I just cleared out the stack. You can do the same by hitting the clear button. And what we're going to do now is calculate the charge using this same formulation for the point inside of the sphere. And we're going to follow the same process. And we know that if we can get the charge density at any location inside that sphere that we assign the 1 coulomb to, it's uniformly distributed, so we should be able to recover 1 coulomb for any location, including the point that we chose, which is directly at the center in this case. So let's go ahead and repeat those steps. We'll probably go through it a little bit quicker now since we've just done it once. So let's remember the quantity was electric field. We hit the divergence of the electric field to start building the stack. We're going to hit geometry and choose a point that's going to be the inside point now. Okay, and then we're going to choose value. So that's going to collapse that expression now into this new expression. And then when we evaluate this, we could do it now if we wanted to. We're going to go ahead and leave it as the expression. That's going to be the divergence at that point. So remember, what we're trying to do is get we're trying to recover the charge at this point, which means we multiply it by epsilon naught and we multiply it by the volume again. So let's go ahead and go to constants, and there's epsilon naught. We can just leave it in the stack like that, and go ahead and put we'll go ahead and put our volume in. If you remember, the number that we calculated for this half millimeter charged sphere was 0.524 times 10 to the negative 9, and that's what we use for the notation. Okay, so we'll multiply these. So we just multiplied, condense it into this value. We'll multiply one more time, and now we should be able to get a value, or I should say evaluate. Okay, and when I evaluate, this is the result of that entire stack multiplied by those two constants. And if you look at the number that we get, it's not exactly 1, just like we didn't exactly get 0, but we got a number very close to 1. So what this says is that if we want to know what the charge is at that given point, instead of the charge density, we multiplied it by the whole volume, we recover that exact same charge that we assigned to that sphere. So what we've done is we went through an analytical derivation of Maxwell's first law, Gauss's law, for a very simple case where we have the electric field defined due to a charged sphere, both inside and out. We came up with these two different values for 0 outside and a rho divided by epsilon naught for inside. And then we went through the field's calculator and ran a numerical verification of similar points, a point inside the sphere as well as outside, and we were able to show that we were able to validate Gauss's law. That's it for the session. Thanks.